The next topic is orthogonal polynomials, section 5.4. So we've talked about spaces of polynomials as vector spaces. So for example, if you let V be the set of polynomials of degree less than or equal to n, this is a vector space. We've talked about this a little bit. What's a basis? Well, the natural basis is the constant function 1, the polynomial x squared, and so on, up to x to the n. So the dimension, of course, is n plus 1. And to say that this is a basis is to say that if you take any polynomial of degree less than or equal to n, it can be uniquely expressed as a linear combination of these, which is its a0 times 1 plus a1 times x plus dot 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 an times x to the n. And that's more or less the definition of a polynomial of degree less than or equal to n. So that's just a reminder of what we're talking about when we talk about spaces of polynomials. And what I want to talk about now is orthogonal polynomials. So we must be talking about polynomials which have some inner product. And the natural inner, well, there are many natural inner products on the space of polynomials. The one we're going to use is the following. We're going to take the inner product to be defined as follows. The inner product of two polynomials p and q is the integral of the two polynomials dt. So before I put in the limits on this integral, let's just think about this a little minute. So, and remember, an inner product is supposed to be bilinear. And integration is bilinear. If you add two polynomials, the integral becomes the sum. And if you multiply it by a constant, and so on, this is bilinear. And it's supposed to be positive definite, which is to say the integral of pp is the integral of p of t squared dt, which is certainly greater than or equal to 0. The only problem is, what am I integrating over? Well, I can't integrate from minus infinity to infinity because most polynomials, that integral doesn't exist. So you basically need to integrate over a finite interval, and up to some normalization, it doesn't really matter. So what we're going to do is we're going to take the integral to be from minus 1 to 1. So this is our definition of the inner product on the space of polynomials, and we'd like to study some properties of these spaces. And I'll just mention that these things come up a lot in applications. For example, in Fourier analysis, where you basically decompose a function into a linear combination of other functions, and many applications of this. So maybe I'll get a chance to talk about a couple of these applications, but for now, let's just look at the mathematics of it, of these spaces of polynomials. All right, so again, let's let V be the space of polynomials of degree less than or equal to n. And the book uses the notation P upper n for this space, but I'll just use V. And let me remind you that we're using the inner product PQ is equal to the integral from minus 1 to 1 of P of t, Q of t, dt. And a basis of this space is the constant function 1 t squared up to t to the n. On the previous slide, I said I used x here, but I'm going to be using the variable t, so it doesn't really matter. You can use whatever variable you want. I'm going to be using t. So, for example, you could ask, what are the properties of this basis? For example, is it orthonormal, or is it orthogonal, or what? Well, what is the inner product of t to the k with t to the l? By definition, it's the integral from -1 to 1 of t to the k plus l dt, and you all know what that is. That's 1 over k plus l plus 1, t to the k plus l plus 1 from -1 to 1. And what is that? Well, if k plus l is even, then k plus l plus 1 is odd, and this comes out to be 2. So this is 2 over k plus l plus 1 if k plus l is even. But if k plus l is odd, this is even, like t squared, for example, and then you'd be getting 1 minus 1, which is 0. So it's 0 if k plus l is odd. All right, well, this obviously is, therefore, this is not an orthonormal basis, but a very natural thing to do is to apply Gram-Schmidt to this natural basis, to 1t, t squared, and so on. So if you do that, what are you going to get? You're going to get some basis, which we're going to write as Q0, Q1, Q2, and so on. And Q0 is some multiple of the vector 1. And so Q0 is some constant. And Q1 is some linear combination of 1 and t. So this is some a plus b t. Let me write this constant. And then Q2 is the first 3. So c plus dt plus et squared, and so on. Qk is going to be a polynomial of degree k. So let's see what we get. Okay, so we're going to start with this basis 1t t squared, and we're going to apply the Gram-Schmidt process to it. And remember, that has 2 steps. You first construct a bunch of orthogonal polynomials, and then there's a second easy step where you normalize them. And I don't care so much about the normality, so let's just do the orthogonal part of the process. So what do? You start off with Q0 is the first basis vector. And the first basis vector is the constant function 1. So that says that Q0 is equal to 1. And you don't have to normalize it. It's just what it is. Now, what about Q1? Q1, so how does Gram-Schmidt work again? So Gram-Schmidt says you start with your second basis vector, which is to say t. And remember, you add some constant times the preceding Q0, and the constant is given by the inner product of t with the preceding guy over the length of the preceding guy. And you got to just be a little careful now. So when you see this, it looks a little funny, but this is 1 as the constant function. So we just have to compute this thing. Well, what is t1? Well, that's t to the 1, t to the 0. So k is 1 and l is equal to 0. And k plus l is equal to 1, which is odd. And when k plus l is odd, this is 0. And on the other hand, 1, 1 is equal to t to the 0, t to the 0, which according to that formula I had a couple of slides ago is 2 over 0 plus 0 plus 1, which is equal to 2. Now, for this formula, I didn't really need this because if this is equal to 0, I'm just getting q1 is equal to t. Okay. And clearly, you can just keep going one step at a time. What's q2? Q2 is what? Q2 is t squared minus t squared 1 over the length of 1 squared times 1 minus t squared t over the length of t squared times t. And what is that? So that's t squared minus, well, let's see, I've already computed this. What's t squared 1? T squared 1, well, the sum of the powers is even, and so this is equal to 2 over 2 plus 0 plus 1, which is to say 2/3. And so what we're getting here is 2/3 over the length of 1 squared, which is to say 2 times the constant function 1. And then this guy is, well, the sum of the powers here, this is, since 2 plus 1 is odd, this term goes away, and that's all you have. So Q2 is given by this formula. And, well, I should have rewritten it as Q2 is equal to t squared minus 1/3. Okay? And you just keep going like that. So I'll just write down a few more of them. Q3 is equal to t cubed. And if you think about it, what happens is there's some kind of alternation. Well, let's write it out. Let's do one more written out, a couple of terms. T cubed 1 over 1 squared 1 minus t cubed t over the length of t squared t minus t cubed t squared over the length of t squared squared t squared. And remember that when the sum of the powers is odd, the terms go away. So both of these go away, and you see that Q3 is going to be t cubed plus some multiple of t. And it turns out to be minus 3/5 t. And the next one is what? Q4 is equal to t to the 4th. And it's only going to have even powers, is the way it works. So you get something times t squared, which turns out to be 6/7. And then the next term turns out to be 3/35 times the constant function 1. Okay, so here are the first few Q's that I just calculated. And now we get to a very important family of polynomials called Legendre Polynomials. And these are essentially the Q's. The kth Legendre polynomial, pk of t, is some multiple of the kth polynomial I just computed, where ck is chosen so that pk of 1 is equal to 1. So this is a lot like making an orthonormal basis. We have an orthogonal basis here. I could have modified each qk by a constant in order to make it length 1. Well, this is a different choice. Here we're choosing we're modifying each qk by a constant and just satisfying this condition. So these are still orthogonal, but they've just been normalized differently. So let's write down the first, and these are called the Legendre polynomials. So let's write down the first few of them. So P0 of t is what? Well, it's 1. And what is this ck anyway? Well, just think about it for a second. What I'm saying is that pk of t is obviously 1 over qk of 1 times qk of t. The constant is qk of 1, so when you plug in 1, you get qk of 1 over qk of 1 is 1. So p1 of t is t. And what is p2 of t? Well, it's t squared minus 1/3 over 1 minus 1/3, which is to say t squared minus 1/3 over 2/3, which is to say 3/2 t squared minus 1/2. And p3 of t is equal to t cubed minus 3/5 t over 1 minus 3/5. And that is to say the constant is 5/2. 5/2 t cubed minus 3/2 t, and so on. And there's actually a formula for ck, which I'll write down. Ck is given by this rather interesting formula, 2k factorial over 2 to the k times k factorial squared. You should see page 251 in the book for the graphs of the first few Legendre polynomials. And I'm just going to mention one other thing about these polynomials. There's a beautiful formula called Rodriguez's formula. It turns out that the kth Legendre polynomial can be realized as the kth derivative of this function t squared minus 1 to the k. And, well, that's actually up to a constant, and the constant is 2 to the k times k factorial. But don't worry about the constant. The main point is, what is this saying? Let's think about this for a second. So t squared minus 1 to the k is what? T squared minus 1 to the k is, if you expand it out, it's some polynomial that starts off with a t to the 2k plus dot dot dot, and then all the way down at the end there's the constant term is minus 1 to the k. And if you take the kth derivative of that, well, the top degree term of when you take the kth derivative, every time you take a derivative, it decreases the degree by 1. So you get some constant times t to the k. In other words, this is some polynomial of degree k. And that's what the kth Legendre polynomial is supposed to be. And so, well, I'm not going to prove this formula, but let's just write down the first couple of examples. So, for example, P1 of t, according to this formula, is 1 over 2 times the first derivative of t squared minus 1, which is 1/2 times 2t, which is t. And P2 of t is equal to 1 over 4 times 2 times the second derivative of t squared minus 1 squared, which is 1/8 times the second derivative of t squared minus 1 squared, t to the fourth minus 2t squared plus 1. And pause the video and please confirm that this is in fact equal to 3/2 t squared minus 1/2. Notice, by the way, looking at this example, you can see when you expand t squared minus 1, you get a polynomial in t squared. So all of these terms are of the same, have the same parity. The degrees are all even, and you're taking two derivatives, and so at the end, the degrees are all the terms are all have even degree. And anyway, calculate that. That's what you get. So Rodriguez's formula, it's actually quite a beautiful proof. I'd love to do it, but I think it's a little bit aside from the main thrust of things. But excuse me, that's part of the proof. But if you want to see see this in the book, it's theorem 5.30. And the more mathematically inclined of you in the class might be interested in looking at that proof. So in order to calculate these guys, obviously the main thing we're going to need to know is what's the inner product of t to the k and t to the l with respect to this inner product. So that is to say, it's this integral. And, well, obviously it comes down to this question. Can you compute the integral of t to the n e to the minus t dt? What is that equal to? Let's see. Does anybody remember how to do calculus? The way you do an integral like this is by parts. You let u be t to the n, so that du is equal to nt to the n minus 1. And you let dv be e to the minus t, so that v is equal to minus e to the minus t. And this integral is equal to uv minus the integral of v du, which gives you, let's see, uv is minus t to the n e to the minus t from 0 to infinity, minus the integral of v du, so you get minus the integral of nt to the n minus 1 minus e to the t dt. So I'll just write down the first few Legendre polynomials. These are, the first one is q naught of t is the constant function 1, and q1 of t is t minus some multiple of 1, and it turns out to be this. And q2 of t turns out to be t squared minus 4t plus 2. q3 of t is t cubed minus 9t squared plus 18t minus 6. So notice a couple of differences with the Legendre polynomials. So one is that all powers occur. Remember, in the Legendre polynomials, only even or odd occurred in a given polynomial. And also notice that the coefficients, unlike the Legendre polynomials, are integers, which is kind of nice. So I think that's a good place to stop. There's a little bit more in this section, but I'm going to skip it. So I'll just write down the first few Legendre polynomials. These are, the first one is Q0 of t is the constant function 1, and Q1 of t is t minus some multiple of 1, and it turns out to be this. And Q2 of t turns out to be t squared minus 4t plus 2. Q3 of t is t cubed minus 9t squared plus 18t minus 6. So notice a couple of differences with the Legendre polynomials. So one is that all powers occur. Remember, in the Legendre polynomials, only even or odd occur in a given polynomial. And also notice that the coefficients, unlike the Legendre polynomials, are integers, which is kind of nice. So I think that's a good place to stop. There's a little bit more in this section, but I'm going to skip it.